So yesterday we learned the main parts of the periodic table. Got just a brief history lesson. Talked about like where did it come from, who figured out how to put everything together. And then we started breaking the periodic table up into parts. And we started off with just two broad classes of elements, which we call metals and nonmetals. We know that there's a little gray area as they transition from one to the other. We call those the metalloids or semiconductors. And then we broke it down even more and we started talking about each group of the periodic table and the special characteristics each group has. We also emphasized how many valence electrons each group has, how many, which tells us if they're a metal, how many electrons the metal will give away. If it's a nonmetal, that gives us an indication as to how many electrons a nonmetal will steal. So we just learned the basics yesterday. And as we were going through and doing the columns, our main columns were the alkali metals, the alkali earth metals. Then we did this whole D block in that area under the stairs. Those are our transition metals. And then we came way over here to the end to group 18 and talked about the noble gases and then the halogens. We didn't give these groups names, but often you'll hear us call this group the oxygen group just because oxygen's at the top, and this group will be the nitrogen group. But the main groups you need to know are the ones that we discussed yesterday. Now today what we're going to do is we're going to talk about some really cool patterns that we see within the periodic table that can help us predict certain things that are going to happen or what things are going to look like. And the first one is atomic radius. And atomic radius is the approximate distance. I do some abbreviating today just to save yourself some space. The approximate distance between the nucleus and the valence electrons. So we all know what radius is. If you have a circle, it's the middle to the edge, right? We'll talk, we know that's what radius is, but when I think of atomic radius, I'm really thinking about the whole atom. I'm thinking about how big around is the atom? Is it a little tiny circle or is it a big circle compared to other atoms on the periodic table? And the cool thing is we have a trend. And the trend is, as we go across a row of the periodic table, any row, atomic radius actually decreases. That means as we go across, they get smaller and smaller and smaller. Now, that might seem sort of weird because as we go across a row, what is the mass doing? It's getting bigger. So as we move across, it's getting heavier and heavier and heavier. But I want you to remember that mass is in the nucleus. And that nucleus is super tight. It's super compact. So we're not really gaining a lot of volume as we go across. But here's what's happening. And you don't need to draw this. I just want to give you a good explanation. As we move across, not only is the mass getting larger, and I'm just using this row, this is true for any row, but the number of protons in the nucleus is increasing by 1 every time we move over. Now I want you to remember the nucleus contains two particles. The nucleus contains the protons and the neutrons, right? And the protons are positive and the neutrons are neutral. They don't have a charge. So overall, this nucleus actually has a positive charge. And the more protons you put in it, the more positive it is. For example, lithium's nucleus has 3 protons. So its nuclear charge would be +3. Neon, though, if you keep going across the road to the other end, neon's nucleus has how many protons? 10. I'm not going to draw all 10, but it's got 10 protons, so its nuclear charge is +10. Now, I also want you to remember that nucleus, which we've all just established has a positive charge, is surrounded by what? Electrons. And what's their charge? Negative. And what do opposites do? They attract. So here's what's happening. For lithium, lithium's nucleus, and I'm again just looking at row 2. That's the one I'm using, true for any row. Lithium's nucleus has 3 protons. But as you start moving across and adding a proton, adding a proton, adding a proton, that nucleus is actually getting stronger because its charge is getting more and more positive. And the more positive that charge, the more tightly it can pull in its what? Electrons. If you will think today, this is so unscientific, if you would think today as the nucleus like the mama, and the electrons, like her rowdy little children, a lot of this will make just good sense. So if that nucleus has a +3 charge, that mama's pulling, she's got a little bit of a rein on her electrons, at least kind of keeping them in check. But as you move across all the way over here to neon, that nucleus is really strong and can pull the electrons in much more tightly. So what's happening is, even though your atom is getting heavier, it's getting more compact. Does that make sense? It's just like kind of the theory that muscle weighs more than fat. Y'all have all heard that. You can have a very muscular person who actually is a smaller size than someone who weighs less because they just may have a lot of muscle mass. So you can kind of think of the atom like that as well. It's just getting more muscular as it goes across, so it's getting more dense. So the note that we're going to write for this is we're going to put it right under here. And we're going to say this happens because the stronger, more positive nucleus, that means it has more protons if you want to make a note of that, pulls in the electrons more tightly. There's a lot of ways you could write that. This is just the way I'm doing it. And because of that, it's basically getting more compact. Because that electron cloud is so fluffy and there's a lot of empty space in it, there's a lot of room for those electrons to be pulled in a little more. So even though that nucleus is getting heavier, since it's so dense, you're not seeing a big gain in the volume of the atom. But again, it's pulling those electrons in more tightly. So as we go from left to right, the radius gets smaller. That is the trend. Now we're going to talk about what happens to radius when you go down a column. So let's say you're looking at column 18 and you go from helium to neon to argon. What's happening to the radius of that atom? Think it's getting bigger or smaller? It's actually getting larger. I'm going to give you a little hint. What's happening as I go down a column? More levels of electrons. Remember, the row tells us how many levels of electrons, right? Helium only has 1 level of electrons, but neon has 2, and argon has 3. If you keep adding layers, you're just going to get what? Bigger, right? If we all put on a big old fluffy coat, we're going to look a little bigger. If we wrap a big old blanket around that, we're going to look a little bigger. So the first reason, there's actually 2 reasons this happens. The first reason is just one that probably makes sense now that I've said it. As you go down a column, you're adding a level of electrons each time, so you're just going to get bigger. The second one's a little more involved, but it's not difficult, and it's actually going to come into play on all the trends. So I'm going to spend a lot of time explaining it on the first one, and then you'll just know it for the rest. The next one is something called electron shielding. And I'll give you an example. Since I was working with group 18, I'll stick with that. I'm going to use neon. So you got neon, and don't draw this. Neon has how many levels of electrons? Neon has 2 levels of electrons, and we know there are 2 electrons on the first level, and then there are 8 on the second level. Okay? Now again, remember, neon's like mama, and the electrons are like the what? They're like they're rowdy children. They're not even just children, they're rowdy little children, okay? Now, as we go on down, let's do krypton. So I'll skip a few. Krypton has how many levels of electrons? 4. But look at this. So here's level 1. Here's level 2. I'm going to exaggerate it a little bit. I'm not going to put all the electrons on it. But y'all know there are electrons on the levels, all over the place. What? It's kind of obvious that's going on there. What'd I do? The spacing's bigger, right? Yeah. Here's why. This mama right here only has 2 levels of electrons to keep up with. So she can keep a real tight grip on the first one because they're right close to her. Second one, they're just a little out, but she can keep a pretty good grip on them too. But this mama has 4 levels of electrons. She can hang on to this first level pretty tight. Second one, okay. But what's happening when she's trying to reach out here to her electrons on the third level? What's happening to her grip? Slipping a little bit, that's a good way to put it, because she's trying to reach through these 2 levels of electrons to reach the third one. And because her grip is not as tight, like any rowdy little kid, if they get out of mama's grip, which way are they going? Away. Yes. So these guys are like, hey, she can't hang on to me as tight. I'm going to move away from the nucleus a little more. And then by the time we get out here, her grip is not very strong at all. That's called electron shielding because the nucleus's hold or grip on those electrons gets weaker and weaker as you get more levels of electrons shielding her pull from this very outer level. If you go to Walmart with like 3 kids, I can keep a pretty good rein on 3 kids. I'm not saying I want to, but I could. I always use Walmart as an example because when my kids were little, that always seemed like where they lost their minds and wanted to misbehave. But with 2 kids, I had 2 arms. I keep a pretty good grip on them. But what if I went to Walmart with 25 kids? I know. First of all, who would want to do that? But the first few, maybe it was a field trip, the first few I can kind of keep my hands on them. But what is happening to the ones out of my reach? Where are they going? Away. And crazy, right? That's what's happening here because all those kids between me and that very outer fringe of kids are being shielded by all those levels in the middle. So that's what electron shielding is. So I hope that that makes sense to you. So we're going to write an explanation here. We're going to have 2 reasons. The first reason that the radius increases going down a column is we are simply adding levels of electrons. That just makes sense. The second reason is called electron shielding. And that means that the levels of electrons between, y'all see my abbreviation there, between the nucleus and valence electrons, I'm going to abbreviate valence electrons, shield the nucleus's pull on the outer electrons. Basically, all those levels are just getting in the way. So we've learned 2 trends for atomic radius. As we go, oh, and anytime I say across is always left to right. And as I say down a column, obviously, that's going down a column. That's all the trends we're going to look at today will always be in those directions. So let's do 2 examples. Number 1, put these in order from largest to smallest. This specific example wants me to put the largest one and then go down to the smallest. So our first example, you see these 4 atoms. Here's the trick on these. Ask yourself, are they the same row or the same column? These are the same column. So I want you to draw a little arrow down. What do we know happens to radius when you go down a column? Okay, so we're going to say increases. So that means my largest ones are going to be where? The top or the bottom? The bottom. So which one's the largest? Barium. What's next? You can just give me the symbol if you don't want to say it. SR. What's next? We're going to smallest. Calcium and then magnesium. So if you will ask yourself the question, are they same row or same column? First thing, that's a lot easier to answer. These were on the same row. And we know that as we go across a row, that radius decreases, meaning my largest ones are going to be over on the far left.